All right, ladies and gentlemen, it's your boy back with another video talking about what's exciting in science right about now. I couldn't help but make this video. I'm working on something else for crypto right now as well, but this is really important stuff, I think, because I've been following what's been going on lately with LK-99, the room temperature ambient pressure superconductor that everybody's talking about, and it's really exciting. Because it's starting to look potentially a bit more promising. We're going to go through basically what is a superconductor and why is this important, why is this something you should care about, and then we'll kind of go through the, frankly, K-drama that has been developing on Twitter. And that seems to be pretty much where everything is going on right now is Twitter. I refuse to call it X. That's absurd. But there's, you know, the latest up-to-date stuff seems to be happening there, and that's where we're getting a lot of this news. I'm going to link the links to a lot of these resources in the description, and you'll be able to go ahead and, you know, read this for yourself. I highly recommend it. Highly recommend it. I'm just going to try and get as much of this in one video in one place as I can right now, as contemporaneously as possible, because this is all kind of happening and updating in real life, like in real time. So let's start with superconduction, okay? Why is this an important concept? So you might not even be familiar with the word. Superconductivity is a state that some metals can enter. Initially, I believe it was discovered with mercury, where you cool it down to near absolute zero, and it experiences a critical transition point near absolute zero, where the atoms are almost not moving anymore. Where it starts to display two important properties of superconductors, okay? One is near zero resistivity. It's not actually technically zero, but you actually more or less think of it as basically zero. It's not actually, but when electrons pass through the material, there's very little resistance. Think of it like a solid metal is just like a lattice work of a bunch of like marbles, and the electrons are tiny little grains of sand that need to make it through the marbles without hitting each other or hitting the marbles. So in a superconducting state, they can just pass right through, and no energy is lost to them hitting each other or hitting the solid that it's going through. So a superconductor doesn't lose energy. It can transmit electrons as infinitely far without losing any energy. This is a huge issue with our technology today, as we'll see shortly. And then the other big property is that it expels magnetic fields from inside of it. In other words, in a superconducting state, a material is actively excluding magnetic fields from inside of it, okay? This means that if you apply a magnetic field to it, it will repel that magnetic field. And so this is where you see superconductors, these demonstrations of them floating, right? They have a magnetic field, and they have this chilled superconductor, right? There's always this gas, and that's typically helium gas, and some superconductors are a higher temperature, but that still requires nitrogen. Sorry, not helium gas, liquid helium that is then evaporating as they pour it to make the superconductor below the critical temperature, and then it starts floating. And then if it's pinned in place, that's another thing that you can see where they make it float, but it just kind of stays in one place, and you can make it spin in place. That's actually an extra thing. Flux pinning, you actually cause some defects in the magnetic field, and then align the magnetic field that you're applying with that in the superconductor, and then it gets pinned in one place where it's hovering. So that is kind of what they talk about when they talk about like the Meissner effect, where it starts to exclude magnetic fields. Those are the two properties that are interesting about superconductors, and these are properties that are only explained by the quantum properties of that material, not the classical properties. So this type of thing it seems like magic, the types of things that you can do with superconductors, simply because superconductors work by different rules than what we're used to even thinking of. But from a technical perspective, this is why they're special. They exclude magnetic fields from inside them, and they can transport electrons without losing any energy. Why is that a big deal? There's a bunch of reasons why that's a big deal. Okay, so the one that's probably the most immediately applicable to most people that you care about is that the price of energy goes down, okay? So you might immediately think of transmission lines, right? Getting electrons from one place to the other, but that's actually only saves, I think it's only like 5% efficiency in the actual lines. The bigger gains are from transformers and generators, increasing the efficiency of, stepping up and down voltages with magnetic fields for residential grid use is actually really important there. And generators and stuff like that, and transformers can get something like, anywhere from like 40 to like 70+% efficiency improvements if you were to introduce superconductors into them. We can't do this right now because you have to cryogenically freeze your superconductors. You need, helium to go near zero, or with some of the more modern ones you use nitrogen, but a lot of those you need to use pressures of like 155 gigapascals, which is a lot. Low temperatures and high pressures are expensive to maintain over a long time. There are high temperature superconducting tapes, but remember, high temperature up until now has basically meant 77 Kelvin, which is still really cold. So high temperature is really low temperature so far. And even the higher temperatures require serious pressures to get to superconduction. So we have these superconducting tapes that are largely a matter of just like extremely good engineering, trying to make them more resistant to all these conditions, but they still require really cold temperatures. And so this applies to a lot of things. Well, so the first thing that you will care about is simply that prices will go down for energy and just about everything, really, because energy is used to make everything. It's in the supply chain of everything, right? If the price of energy goes down across the board, which is very much what we're going to see here if this is, continuing to be replicated and show promise, the price of energy goes down across the board. So yay, that's cool. MRIs is another interesting one. So MRIs are magnetic resonance imaging that we use in medicine all the time. They use these really strong, like 3 Tesla magnetic fields to align the protons, basically mostly in the water in somebody's body. And when those protons, align their spin with the magnetic fields, then they emit radio frequency waves that are then picked up by the sensor and constructed into an image, okay? There's a couple of ways that this helps with MRIs. One, modern MRIs shield the magnetic field with superconducting coils that kind of shield the magnetic field from the outside. But you need liquid helium to keep those at cryogenic temperatures. This increases the cost of the MRI. And so if you don't need that cryogenesis, the price of MRI goes down significantly. But then also using superconductors in the actual MRI itself increases the sensitivity of it but by reducing the noise in the sensors. We're actually going to talk about that next. Actually, why don't I mention that right now? Part of that is also reducing what's called the Johnson-Nyquist noise. And this applies to all sensors, not just MRIs. So any sensor has to deal, especially when you're dealing with very sensitive measurements, especially when you start looking at quantum measurements and stuff like that. The electrons hitting each other, like in the sensor itself, actually kind of matters. This is kind of an oversimplification of what the Johnson noise really is. But it's the thermal noise that comes from electrons hitting each other that messes up, to some small degree, all sensors. Part of this being eliminated will make all sensors more sensitive, including MRI. And we wouldn't need helium, which is a non-renewable resource. That's a really big deal because we can run out of helium. We're gonna run out of helium. It would be terrible if we could no longer do MRIs when that happens. This is a big deal for that. Maglev trains. Let's talk about maglev trains. So the other thing about why maglev trains, trying to use superconductors for that is cost prohibiting because once again it has to be cryogenically frozen to basically keep the superconducting going. So maglev trains with superconductors cheaply made with LK-99 at room temperature, you could then much more cheaply build out an infrastructure of maglev all around America so that continental travel becomes dramatically faster. 14,000 miles an hour, by the way. You can go to like New York to LA in like 20 minutes. Cheaply. Think about that. Cheaply. That's really something. Another similar thing there is quantum computing, right? So if you ever see a picture of a quantum computer, you see all this stuff, and all that stuff is mostly cooling apparatus. Cooled helium and stuff like that that are meant to keep the actual chip as close to absolute zero as possible, okay? One of the big applications for a room temperature superconductor is you could eliminate all that cooling equipment. The actual quantum computer is like small. It's not that big. But if you look at a quantum computer now, you see this whole big apparatus. Most of that is cooling. As soon as you have room temperature superconductors, you don't need that cooling apparatus. That's the point of most of that equipment, is to just make sure we have superconductivity that we can use in the actual chip. You don't need that anymore. Now you can have desktop personal computers with the room temperature superconductor. That's really awesome. Desktop quantum computers. And then of course there's nuclear fusion, the other miracle technology. We got ignition back in December 2022. And you know, that's really impressive. This is probably going to accelerate that a lot, because one of the main challenges in fusion is that you need, so the magnetic coils that you use to actually generate the magnetic field used in to contain the fusion in the plasma, you use superconducting materials for that, which means you have to cryogenically cool that to near absolute zero. But the plasma that you're using for the fusion is like 1,000,000 degrees, right? So really what you're trying to do in a fusion reactor is you're trying to take this 1,000,000 degree hot plasma and this near zero cryogenically frozen magnetic coil, and bring these two things as close as possible without destroying either of them. That's an enormous challenge. And it would be really great if you didn't have to constantly keep the superconductor cryogenically frozen the entire time. This should dramatically decrease the amount of energy that will actually be required to make fusion work. That's kind of a big deal. If we were able to engineer our way to ignition without without room temperature, ambient pressure superconductors, I feel like at this point that's going to give us a lot of extra headway, because we're already doing pretty good. And of course, finally, hoverboards and stuff like that. I mean, obviously, so Back to the Future, thought it was going to be like 2015. Well, we got this in 2023, so maybe less than 2 decades off. 2 decades off. That's optimistic. Let's be serious. More like 3 decades off, because it'll take a while to actually, do a lot with this. They have to build a lot of infrastructure to make these things happen. And on the outside end of this, I mean, if we're talking about less practical, not in anywhere in the near term kind of thing, this outside end of what this technology scales to is borderline magic. All right, like apparently there's a way that you can use these to create columns of effectively infinite compressive strength, such that you can use them to create superstructures in space that don't collapse under their own gravity. So this would be one of the basic technologies that you would use to create a new planet from scratch. Once again, not something we'll be able to do anytime in the near future. You still need to design self-assembly in space and space mining. So there are teams working on that self-assembly, as Neil Gershenfeld at MIT, and space mining. Actually, there's multiple companies these days trying to get that started. So that's super interesting. That's why I think you should care about superconductivity, why this is a really huge deal for you. This is a discovery on par with the transistor. The Nobel Prize for the transistor was, I believe, like 1956. A lot of the difference between the technology in 1956 and the technology of today is the transistor. This is going to make an even bigger difference than that. So get excited. So, like I said, I'm going to link the full resources on the Twitter stuff in the description here. But basically, it seems like there's this story that's going on in South Korea right now, where there's these guys, there's Lee, Kim, and Kwon. These are the guys that more or less came up with LK-99. LK-99 actually stands for Lee and Kim 1999, the year that they first synthesized it and their names. And it was originally them. Actually, originally, there was this guy named, I guess, T.S. Chair or something like that, who was their lab advisor, like their teacher, basically. And he had been doing a bunch of work with superconductors and way back, decades ago, apparently he had like a blip in his data that he never ended up pursuing simply because, you know, it was like a blip in the data that could really be just a measurement error, and really he didn't have the money to really pursue it rigorously and didn't think it was necessarily worth that. And his PhD student, I forget if it was Lee or Kim, but he didn't choose to do it for his PhD, presumably because he was more practical, and it never really panned out in the past to go all in on trying to find this room temperature superconductor, because T.S. Chard apparently spent a lot of his career trying to come up with like this theory of like a one-dimensional superconductor that should behave like this, and he ended up dying without finding it. However, near the end of his life, he got two of his students, Lee and Kim, to come visit him on his deathbed, and he tells them, and remember, this is all kind of the secondhand story that we're trying to kind of getting right now in real time as people are digging into this. He tells them, I have this feeling about this result that I didn't follow up on years ago. I want you to go and track that down and see if it's real. And I guess that's what they ended up doing. Well, one of them had like a wife and kid, and he couldn't like go until I think it was Lee went to get the money. So he gets the American guy, Kwan, who I believe is a physical chemist, who has he's American. He brings the NIH funding, basically. So he got him on board, and so now they're like, okay, we have funding, so let's go look for this. And apparently they did like 1,000 experiments. And this is really interesting because some of these people are physicists, and then this guy is like a chemist, right? And so the difference in approach is really hilarious, right? Because more recently, the chemist is kind of like dunking on the physicist because like he's South Korean, so he's very polite about the whole thing. But he's basically like, look, this is just a skill issue. You should have just tried harder. I know you physicists like to sit around and just like, you know, write out your equations or whatever, but I'm a chemist. I make things, right? I just went ahead and made the superconductor. You know what I did? And he just laid out this really simple step-by-step instruction on like how to find a superconductor. And it was very polite, but like low-key, like condescending a little bit. It was awesome. But basically, yeah, so they get to work on finding LK-99 by basically just randomly trying things. Somebody on Twitter did the math on how crazy that actually is, to just brute force different materials until you find the cheat codes for reality, which is what these guys basically just did. It should have taken them something like 100,000 or 1,000,000 years or something, and they did it in 20, which is insane. I mean, Quan will straight up brag that he did like 1,000+ experiments for this, but if it didn't work, that's the craziest idea possible. Like, you can't tell them anything now because they were successful, but without knowing that a priori, you would think that's a dumb thing to do. Why would you do that? Well, it worked. They just randomly tried stuff until they found a superconductor. Finding the superconductor apparently was quite an issue because there's apparently a machine called the ERS machine, and only one person, the chemist on the team, is the only one who knew how to actually use it. And that was the expensive thing, so they had to get the funding for that, and then eventually they find it, and at some point in 2018 or so, I believe, or 2019, there's this guy named Ranga Diaz who also claimed to have found a room temperature superconductor, but he turned out to be quite fraudulent. And they had submitted their paper with the LK-99 findings way back then, but were dinged in Nature simply because of Ranga Diaz, apparently. And they just weren't able to get their stuff published in that big journal because of the controversy. And so they went and said, you know what, we need to do more characterization and be more sure. And so for the past few years, they've basically been working on the manufacturing process, which has been a big issue because they found what their professor was working on, but they could not replicate it, right? Apparently the key to replicating it was that at some point when they were transferring the quartz crystal that they were, the quartz tube that they were cooking it in, They were transferring it, and it broke at some point at exactly this one time. And it just happened to cause exactly the reaction that they were looking for. It was completely by accident, this discovery. And basically they had to try and recreate this breaking at that same point in that temperature to try and recreate what was going on there. And apparently, so they kept trying to do this. They got their manufacturing process a little better, and they're making more of the material more consistently. But apparently like 4 months ago or something, Kwon had some kind of fallout, some argument with the people on the team, and he was fired 4 months ago. And I guess as part of okay, so this is speculation, but probably a bid to try and keep his name on the Nobel Prize, he leaked the paper. So the paper is not actually, the papers that have been released, they didn't plan on releasing them. Kwon released them, but I can't speak to his intentions, but supposedly they weren't actually ready. And then a second paper was released by Hyun-tak Kim and Lee without Kwon's name. So you know, there's this whole kind of drama going on that we can only kind of surmise what the intentions are behind all of this. Presumably, so the first paper was the 3-author paper. There's speculation that there's 3 authors because the Nobel Prize can only be split 3 ways. And to be fair, that I like that because it shows their confidence, right? Because these people are fighting over a Nobel Prize that they feel that they know they've won. They're that confident that this is a room temperature ambient pressure superconductor. They're already fighting over the credit. These are actual established scientists fighting over the credit. They know what a diamagnet is. I don't think they would have let that fool them, you know? But yeah, basically. So these 2 papers have been released, one with 3 authors, one with 6 authors. They've made a correction to them recently, the 6-author one. They're working to make sure everything is as clear as possible so other people can replicate. But it was released before it was ready. And so then there's this whole drama of like, should one of them be valid or the other and whatever, and then trying to replicate. So this, as soon as it was released, it set off this firestorm of, wait a second, is this real? This is probably not real, right? And you look at the methodology of this, and you would think that if you were trying to fake something, it should be hard to do, right? Ranga Diaz said that his thing could only be replicated at 10,000 atmospheres to try and delay replication. That's a really high pressure. It's going to be hard to even get the equipment for that, right? This, you just put like 4 materials together in a pot, in a vacuum sealed pot for like 1,000 degrees for 2 days and you're set. That's it. That's all you have to do. It's easy. Like, I mean, it is more complicated than that. That's an oversimplification. And realistically, probably little parts of it are maybe left out. They have to really clarify because we'll get to it. We'll get to the replication attempts. But so Twitter goes alight, right? Because the scientists are all coming on and wondering, like, is this for real? And it looks kind of legit, but there's a couple of points of data that are kind of odd. And over the course of yesterday night, most of these were kind of hammered out and a bunch of replication attempts started going through. The first replication attempt that publicly went on Twitter, that is currently being live streamed, by the way, Andrew McCaleb of Varda Space Technologies is basically live streaming him trying to synthesize this in his, like, you know, just his garage or whatever the heck. His lab at his engineering company, because they have the equipment. It's apparently really easy to do. A bunch of other aerospace engineers and Andrew McCaleb and other people are all get on board to try and replicate this. Andrew McCaleb is live streaming his replication attempt. I think Tuesday. I think today we'll know the results of that. They have a video that the original Korean authors released, like a 25-second video of superconduction with the Meissner effect. That video wasn't very convincing, but since then, let's talk about the replication attempts. So Iris GB, this Russian molecular biologist who basically trying to use like kitchen tools and a furnace in her living room to replicate this stuff. And apparently she replicated it. Hers, supposedly she gave screenshots, no video for some reason, but screenshots. And apparently they have superconductivity. She apparently did it just to prove that she could do it better than the original authors. Good for her. That's awesome. That's freaking awesome. That's amazing. And then there were some other replication attempts. Apparently like 4 in China were unsuccessful and 1 in India was unsuccessful. There was a semiconductor part, alternate failure, I think in one of the Chinese ones, where they produced a semiconductor as opposed to a superconductor. And then more recently, just now actually, a Chinese team released a video where they introduced a magnetic field, changed the direction of the magnetic field, and it seems like that's a successful claimed replication. And people in the background are going, holy crap, this is history in the making. A video can be faked. A video can be faked. We need to not get overexcited yet. Argon labs and stuff like that are probably going to be the real replications that matter. But even then, replication is not the end-all of this, because they have that big sample that they originally made float with the presumably Meissner effect. That sample was fairly sized. If they break that up and send that to people and we can at least confirm that that works, then replication simply becomes a matter of, okay, we need to make this. We know it's possible, but if people are failing, then they're doing it wrong, right? If we can prove that that original sample is for realsies and we're starting to think it is, that's a wrap. Nobel Prize, instantly. And it seems like probably it's for realsies. Another piece of evidence, the National Laboratory at Berkeley has now done an in silico simulation of the structure of LK-99 that we've characterized so far, and it seems as though they've now come up with a potential explanation for the superconductivity and a theory as to why we're getting these inconsistent results. So what we're seeing is that LK-99 is basically a modified lead apatite molecule with a lattice of these lead apatite with some lead. Okay, one of the ingredients is lead, basically. Well, it's a compound that includes lead, and depending on where in the lattice that lead substitutes, you either get a superconductor or a semiconductor, and it has to be in that exact position. So this is a really interesting thing. We're going to now talk about, I guess, the limitations potentially, even if this does come out as a room temperature ambient pressure superconductor. Okay, potential limitations. One is that it potentially doesn't allow too much current to actually pass through it. The currents that were actually tested in this, admittedly with small samples and all that like that, and maybe we can scale this up and fix this problem. There's some very small currents that they were actually able to run. So we would need to be able to run more than the millivolts or whatever that they ran through it. So we'll have to address that. The other is its manufacturing process, which they are still very much trying to refine. That's what they've been working on apparently behind the scenes the last few years. It seems as though the team is really just making successful LK-99 like 1 in 10 times. It's apparently really finicky. So we have to decide, okay, so is it just really hard or is it truly random? Because that would really limit its usefulness if manufacturing it really has an element of true random in it, that substitution can't actually be controlled. Now, I'm hopeful that we won't run into that situation. Usually, even with trying to engineer an enantiomeric excess in certain racemic solutions, like that type of thing has been slowly getting better with time. Even if we struggle with that at first, I suspect we'll be able to get that substitution more consistently in the right place so that we can produce a superconductor instead of a semiconductor. But those are some immediate things that stand out to me as potential concerns there. We would need to be able to run more current there, and we need to be able to make it in large quantities quickly and reliably. But otherwise, I mean, the miraculous part about this is that presumably its critical temperature is at least 127 degrees centigrade, which is above the boiling point of water. That's nuts. Now, if you look at the actual graph that they generated for its superconductivity and how much there is, with temperature, obviously, you expect it to superconduct less, and by the time it reaches anywhere near 127 centigrade, there's much less superconductance. It's very weak at that point. But there's still some, which is really nuts, because that means you can literally put this stuff in boiling water and it will superconduct. That's That's crazy. That's nuts. So, I mean, I think that's mostly what I have to say. I highly encourage you guys to go ahead and look at the stuff that I'm going to put in the description. Super fascinating. I'm going to keep looking into this, but it's potentially history in the making. It's potentially really, really going to change all of society forever if this continues to go in this way. So, fingers crossed. We shall see. Peace.